A multi-tenant fabric must do two things at once: connect every authorized path and preserve every forbidden boundary. VXLAN supplies many forwarding contexts, while evpn route targets control which routes enter each context. The rejected assumption is that unique VN is create complete isolation. They do not. A mistaken route target, shared VRF, border policy, or default route can join tenants despite distinct tunnels. The core learning is this: tenant isolation is a deliberate mapping from identity to import policy to forwarding context, and both connectivity and non-connectivity require packet proof. Here is our agenda. First, we shall separate tenant identity from addressing, because two tenants may legitimately use the same prefix. Second, we shall give route distinguishers and route targets their distinct jobs. Third, we shall map Layer 2 and Layer 3 VN is to MAC and IPVRFs. Fourth, we shall build controlled leaking for shared services. Fifth, we shall place external reachability at an explicit border. Finally, we shall prove one allowed flow and several forbidden flows, including overlapping addresses. The objective is a boundary contract, not a table of identifiers. Tenant identity is administrative, not numerical. Customer Blue and Customer Gold may both own 10.0.0.0/8. BGP can carry both because each VPN route has a route distinguisher, and the receiving system installs each into a different VRF according to route targets. Global uniqueness is required for the control plane key and the forwarding context identifiers, not for tenant addresses. Therefore, an address-only test is ambiguous. Every verification record must name the source VRF, destination VRF, relevant RTs, ingress interface, and VNI, as well as the IP endpoints. An RD changes the BGP key. An RT changes the policy decision. If two origins advertise the same tenant prefix with different RDs, BGP can retain both paths as distinct VPNNLRI. If a receiving VRF imports the attached RT, the route may enter that VRF. One route may carry several RTs. One VRF may import several RTs. This flexibility enables shared services and also creates the principal leak hazard. Do not audit isolation by inspecting VN is alone. Export one test route, record its RD, and complete RT set. Then list every local VRF that imports it. A usable tenant service has 4 linked allocations. The tenant maps to one or more VRFs. Each VRF has explicit import and export route targets. Each MAC VRF maps a bridge domain to an L2 VNI. Each IP VRF maps routed overlay traffic to an L3 VNI. RDs provide route uniqueness at the origin. These values may be auto-derived, but the resulting mapping is still a design contract. A configuration generator should reject duplicate VNIs, unintended ERT reuse, missing L3 VNIs, and asymmetric import or export. The allocation registry is part of the security boundary. The L2 VNI identifies a bridge context. The egress action is based on a destination MAC, local attachment, remote VTEP, or replication list. The L3VNI identifies an IP VRF. The egress VTEP performs a tenant route lookup before delivering into a local L2VNI or routed attachment. Confusing these contexts produces subtle failures. A host route may exist in the correct IPVRF while its MAC binding sits in the wrong MAC-VRF, or a packet may decapsulate into a shared default VRF. Capture the VNI and inspect the selected table at decapsulation. Isolation is easiest to reason about when unrelated tenants share no import route target. A blue route carrying RT65000:10 reaches the BGP process on every route reflector and leaf, but gold does not import it. This is an important distinction. Global evpn visibility can coexist with local tenant isolation. The negative proof has 3 layers. The blue NLRI may be visible in the global evpn table. It must be absent from gold's imported IP, or MAC-VRF. It must also be absent from gold's kernel and hardware forwarding state. Finally, a gold packet to the overlapping address must not reach blue. Route leaking deliberately crosses a boundary. Treat it as a new service with an owner, direction, address family, prefix set, next hop model, and rollback. A shared DNS resolver may need routes from tenants to the service and a return path from the service to each tenant. It does not need blue to import gold. A dedicated shared services RT can express membership, but import must still be filtered to the required prefixes. Record route provenance, so a leaked route is not exported again into another tenant. The safe design is a narrow graph of authorized relationships, never a universal transit VRF. When tenants overlap, simply leaking both copies of 10.1.1.0/24 into one shared VRF is ambiguous. The service needs another discriminator. Network address translation can create unique service-side identities. Separate service interfaces or per-tenant VRFs can preserve the original addresses while retaining context. An application proxy can terminate each session on a tenant-specific listener and make an explicit upstream choice. Whichever model is chosen, return traffic must carry the same tenant context. The proof uses simultaneous flows from identical source and destination addresses in 2 VRFs and verifies that replies return to the correct origin. External reachability needs an explicit boundary device or function. A border leaf imports selected tenant prefixes from evpn and exports them toward a firewall, WAN, or Internet Edge. In the reverse direction, it imports approved external or default routes and originates them as Type 5 routes into the intended tenant VRF. The border must preserve tenant identity through separate VRFs, sub-interfaces, labels, or another explicit handoff. A default route is especially powerful. One accidental RT can provide a tenant with unintended egress. Audit both directions, including next hop resolution and the return route. Outbound success alone does not prove a correct service. A Type 5 route cleanly advertises an IP prefix without an endpoint MAC. It may use the advertising border VTEP directly or resolve through a gateway IP, ESI, or other overlay index. None of those fields states that the prefix is safe to leak. Border policy must reject unexpected defaults, more specifics, private or infrastructure ranges, and routes carrying the wrong tenant, RT. Maximum prefix limits bound accidents, but do not replace filters. Verify the selected path. Routers MAC, L3VNI, VTEP next hop, and installed tenant route. Then, withdraw the external source and prove that the dependent route leaves. Dual stack does not mean one proof applies twice. IPv4 uses ARP, IPv6 uses neighbor discovery, and may also depend on router advertisements, link local addresses, duplicate address detection, and multicast handling. evpn can advertise IPv6 bindings in Type 2 and IPv6 prefixes in Type 5, but proxy ND is a separate procedure with implementation constraints. Define equivalent prefix filters and route target policy for both address families. Test allowed and forbidden traffic independently. A deployment in which IPv4 is isolated while an imported IPv6 default or neighbor entry crosses the boundary is not a secure dual-stack tenant service. Begin with a route graph. Select one representative local, leaked, and external prefix. At origin, record its RD, RTs, VNI, next hop, and source policy. At every potential consumer, record whether imports should occur. For expected imports, follow selection and resolution into the software and hardware VRF. For forbidden imports, prove absence from the tenant table and forwarding plane. Then send the matching packet in both directions. This sequence distinguishes distribution from authorization and authorization from realization. Keep overlapping addresses in the test set, so every observation must include the VRF and ingress context. For each positive test, write at least one negative twin. If blue reaches its DNS service, gold must not reach blue through that service. If a tenant receives an internet default, it must not receive an infrastructure or another tenant prefix. If overlapping hosts communicate inside their own VRFs, neither flow may appear on the other's attachment. Capture counters and packets at ingress, border, and egress. A timeout alone is weak evidence because many unrelated defects cause silence. Strong negative proof shows the route was not imported, the forwarding object was not installed, and no matching frame or packet crossed the forbidden boundary. The core learning is this: multitenancy is an import policy and forwarding boundary discipline. Tenant identity maps to VRFs, RDs keep overlapping routes distinct, RTs grant membership, L2 and L3VN is select bridge and routed contexts. Route leaking and external access are explicit new relationships, not exceptions to document later. For every service, name the owner, permitted direction, prefixes, address families, next hop model, and rollback. Then prove the allowed route and packet, and prove the forbidden route, forwarding object, and packet are absent. Do not trust isolation, because identifiers differ. Audit the complete mapping and try to break it.